Black hole megabursts, the most powerful explosions in the universe. Massive stars do not quietly fade away. Instead, some of them vanish in the most violent and luminous explosions our universe has ever witnessed. Recently, astronomers have uncovered a new class of such extraordinary outbursts, events that outshine all known stellar explosions in both intensity and duration. These are known as extreme nuclear transients, or ENTs. Each of these cosmic flares releases more energy in just 1 year than our Sun will emit across its entire 10 billion-year lifespan. That's not a metaphor. That's the literal comparison drawn by researchers who analyzed these ultra-powerful phenomena. According to astronomer Jason Hinkle from the University of Hawaii at Manoa, ENTs redefine what we understand about energy release in the cosmos. Unlike common transient events, which flicker and fade over days or months, ENTs stretch over many hundreds of days. Their radiant glow intensifies for over 100 days before peaking, and then takes another 150 days, or more, to diminish to half of that luminosity. And their peak brightness is nothing short of staggering, 30 to 1,000 times brighter than the most varied types of supernovae we've observed so far. But what causes such unmatched brilliance? The evidence points toward an extraordinary kind of tidal disruption event. These occur when a star ventures too close to a supermassive black hole. The black hole's immense gravitational pull tears the star apart, pulling stellar material into an orbit around it. That material heats up, releasing a torrent of X-rays, ultraviolet rays, and visible light. Typically, these events involve stars less than twice the mass of the Sun and last only a few months. But ENTs are not typical. What the new research reveals is something even more dramatic. ENTs likely arise from stars 3 to 10 times the mass of the Sun being shredded by black holes around 250 million times more massive than our Sun. The scale is almost unimaginable. The gravitational destruction in such encounters is exponentially more intense, resulting in light shows that far exceed those from even the most energetic known supernovae. These flares carry 2 to 10 times the energy of the most powerful stellar explosions previously recorded. But these explosions aren't just bright, they're also deeply informative. The light signatures from ENTs indicate the presence of hot gas and dust lingering near the supermassive black holes. This suggests that the black holes involved aren't dormant, they're active. This is particularly significant because most previously studied tidal disruption events have been seen in inactive, or dormant, galaxies. Until now, scientists only theorized how these cataclysmic events might link to the galaxy-shaping forces of active black holes. With ENTs, that theoretical bridge becomes observable. Astrophysicist Taeho Ryu, from the Max Planck Institute for Astrophysics in Germany, who was not part of the study, sees this as a breakthrough. He notes that ENTs provide a rare opportunity to connect two distinct astrophysical phenomena, the violent shredding of stars and the active role of black holes in shaping their host galaxies. In other words, ENTs offer a unified lens through which to understand both tidal disruption events and galactic evolution in one go. However, ENTs remain rare. Statistically, astronomers expect only one ENT for every 10,000 standard tidal disruption events. Despite this rarity, they remain our best observational windows into the behavior of truly massive black holes, especially those that usually remain silent. These findings could reshape how scientists study the interplay between stars and black holes, and how such explosive encounters influence the architecture of entire galaxies. They may even hint at new astrophysical processes that haven't been fully considered. In the vast silence of the universe, where most things unfold over eons and in darkness, ENTs are loud, sudden, and blindingly bright. They remind us that even in the emptiest corners of space, titanic forces are still at work, tearing, shaping, illuminating. And each time one occurs, it may be the only chance in a generation to witness what happens when a megastar meets its end at the hands of a cosmic giant. Mission to Sedna: How new propulsion could reach the edge of the solar system. In the vast outskirts of our solar system, beyond even the icy orbit of Pluto, drifts one of the most enigmatic objects astronomers have ever found, Sedna. This distant, reddish dwarf planet follows an extreme elliptical orbit that takes more than 11,000 years to complete a single revolution around the Sun. And now, for the first time, scientists are seriously considering a mission to reach it, using propulsion systems unlike anything we've used before. Sedna isn't just another remote celestial body. It belongs to a newly identified group of solar system objects called sednoids. These bodies, with their extraordinary orbits, may represent the first members of the inner Oort cloud, a hypothetical region far beyond Neptune thought to harbor icy remnants from the solar system's formation. Sedna's very existence challenges our understanding of the solar system's structure and the gravitational influences that shaped it. Its orbit alone raises questions. But Sedna's surface adds even more mystery. It has one of the reddest hues observed in the solar system, hinting at complex, perhaps even organic, chemical compounds coating its icy crust. With surface temperatures never exceeding -240 degrees Celsius, it ranks among the coldest known places orbiting our Sun. And it's approaching a rare moment in its orbit that won't happen again for thousands of years. Between the years 2075 and 2076, Sedna will reach its perihelion, its closest point to the Sun. Even then, it will still be an astounding 76.19 astronomical units away. That's more than 76 times farther than Earth is from the Sun, and nearly 3 times farther than Neptune. After that brief approach, Sedna will begin its slow retreat back into the frozen darkness, not to return for hundreds of generations. This fleeting opportunity has triggered new interest in exploring Sedna directly. A recent feasibility study has proposed 2 radically different propulsion technologies that might make a Sedna mission possible, if we act quickly. The first is the direct fusion drive, or DFD, a conceptual engine that could harness nuclear fusion to generate both thrust and electricity. In the proposed model, the DFD would operate at 1.6 megawatts, delivering consistent thrust and specific impulse over time. It represents a dramatic leap beyond anything current propulsion systems can achieve. If realized, this technology could push a spacecraft to Sedna in about 10 years, including 1.5 years of sustained thrust. The second concept is a revolutionary twist on solar sailing. Instead of using only the Sun's radiation pressure, this design uses a mechanism called thermal desorption. By heating a specialized surface, atoms or molecules attached to it are released, creating forward momentum. This method would be enhanced by a gravity assist maneuver around Jupiter, leveraging the gas giant's immense gravitational pull to catapult the spacecraft toward Sedna. The result? A journey time as short as 7 years. Despite their very different approaches, each system brings distinct advantages and trade-offs. The solar sail with thermal desorption is faster and doesn't rely on heavy fuel, making it ideal for a swift flyby. But the fusion drive, while slower, could allow for orbital insertion, enabling long-term study of Sedna, from surface mapping to chemical analysis and the search for moons or other features. Of course, both propulsion methods remain theoretical to varying degrees. The direct fusion drive has yet to overcome major technical challenges in fusion containment and energy control. While some models suggest it could get a 1,000 kilogram spacecraft to Pluto in 4 years, building such a system in practice is still far from certain. Meanwhile, the solar sail with thermal desorption is based on known solar sailing principles but adds a complex twist. It requires precisely timed maneuvers, novel materials, and exact control of thermal release. It's a more evolutionary step, potentially more achievable with existing technologies, but still presents significant engineering hurdles. Time, however, is not on our side. With Sedna's closest approach happening just 5 decades from now, the launch window to intercept it is narrowing quickly. Missions like this can take decades to plan, fund, build, and launch. If we hope to study Sedna up close, we must decide soon whether we're willing to invest in these next-generation propulsion technologies, and whether we're bold enough to explore the outermost edges of our solar system. Sedna beckons as a messenger from the dawn of the solar system. It holds secrets buried in ice, secrets about how our cosmic neighborhood came to be, and possibly about the forces that shaped its very structure. Will we reach it in time?